Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions by email. As I think you may know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about various technologies and certainly the extra design and engineering value that is added by a custom manufacturer such as Quantic Corry. To begin today's session, I'm happy to introduce Quantic Corry's Divisional Operations Director, Bob Meilleur. Bob is an electrical engineer with 30 years of experience developing custom applications for a wide range of filter products. He's written numerous white papers on the subject and has been with Quantic Corry since 2002. So welcome, Bob. Can you share an overview of today's topic and your objectives for the session?
Sure. Thank you, Paul. Today we'd like to talk about feed-through filters and kind of how they're used and why they're used, and hope to share some information to the world out there because we live in a very noisy environment and it gets worse every year. And we have just the fix for that problem.
Well, terrific. And maybe to get started, how would you best define feed-through filters?
So feed-through filters are a component that allow either power or signals to enter into a device where either the power or the signal is not impeded with EMI, electromagnetic interference noise, from the outside world, so that it doesn't interrupt the functions of the circuitry inside the boxes.
Okay, well, thank you for that. And what types of material are these filters typically made from?
Yeah, the feed-through filters that we provide are all ceramic dielectric based. They use class 1 and class 2 type ceramic materials. And those materials, they offer a unique advantage of allowing a fairly high dielectric constant. Therefore, you can achieve some fairly large filtering capacitance values. They have a very, very good voltage characteristic.
I see. And I've heard you say that there are certain requirements associated with feed-through filter applications. Can you explain a little bit?
Yeah, when you're looking at a particular application, there's three things that you really need to take a look at what you need to accomplish. The first is the cutoff frequency of the filter, and that's essentially the frequency at which the filter starts to perform its filtering capabilities. Everything below that frequency, it doesn't impede. The second is insertion loss, and we can get into a little more detail there here in a minute. And then, of course, we mentioned that ceramics are good power material, so the power requirements are a need to know when designing these.
Okay, well, maybe then could you start by sharing a few more details about cutoff frequency?
Yeah, like I said, cutoff frequency is the frequency at which the filter begins to actually work. These are low pass devices, meaning up to the cutoff frequency from DC all the way up to the cutoff frequency. They essentially allow the power or the signal to go through the device without any loss of the signal or the power. After the cutoff frequency, the filter starts attenuating the signal and provides a protection of the higher frequencies from entering through the device into the box.
Got it. So if you could tell me, how does the cutoff frequency relate to other operating frequencies within the device?
Well, again, the cutoff frequency can't be too low in that if say you're running something at a megahertz, and that's a signal that you're trying to pass into the device, you can't have a filter that rolls off before a megahertz. Otherwise, you would be eliminating the signal that you're actually trying to allow in. So you have to, all the signals that you want the device to pass have to be below the cutoff frequency. That's the simple definition.
Well, simple is often best. How about insertion loss then? What would you tell us about that?
Yeah, insertion loss is the amount, think of it, you put the filter in, if you don't have anything there, everything that is in the outside world would enter into the unit. Insertion loss is the function of power out, power in versus power out. And it's a logarithmic function, so it's expressed in decibels. And what you need to look at is if you know that your unit, say, has to pass a megahertz signal, but it's susceptible to a 10 megahertz signal would cause problems with the function of the circuitry, then you need to have some amount of insertion loss at 10 megahertz. The amount of insertion loss that you need depends on how much power you're able to live with inside the unit. So these are all considerations when you're looking at the filter and the different types of filters that there are.
I see. Could you maybe give us an example?
Yeah, so when you look at insertion loss, it's measured in decibels. And for every 3 decibel of loss, you cut the power in half. So if you're down 3 dB, you only have 50% of that noise entering the unit. 3 dB is not very much for a actual feed through filter. It is actually the 3 dB point is defined as the roll off point of the filter, where the filter actually begins. It's not atypical that many of these filters can measure 40, 50, 60 dB and higher. And just for equation purposes, at 40 dB, you've removed 99.99% of any of the interfering frequency that may enter the part.
Well, what then could you tell us about power requirements?
The power requirements has a bit to do more with the size of the part. For all applications, it's an electronic component, so it needs to operate at a certain voltage. And since it's a feed-through part, it needs to also carry through a current, some defined amount of amperage. And when you look at the power requirements, those are essential in determining the size of the part. The current is defined by the size of the through conductor. It's a solid internal conductor. So that conductor has to be large enough to handle the amount of current the device needs to handle. And then, like I said, there's a lot of different voltages that can be applicable to these parts, anywhere from really, 1 volt or even under 1 volt, all the way up to voltages over 2,500 volts.
Okay, and it seems that I've also heard you speak about some of the different circuit options. Can you explain a little more about that?
Yeah, in the type of feed-through filters that we build, there's really 3 different types that are common. And those types are C, L, and pi circuitry. What those have to do with is the number of elements within the filter itself. And I can get into that in a bit when we look at some of the diagrams.
Okay, well then maybe you could explain a little bit more here as we go forward.
Okay. So again, the thing that drives the filter is the total capacitance of the device. That's what is used to set the cutoff frequency. And as the capacitance goes up, the cutoff frequency goes lower and lower. There's different types of ceramics that are used. Mainly they're tubular or discoidal. Discoidals is more of a multi-layer device. It looks kind of like a donut, but there's multiple layers in it, and you can achieve very, very high capacitance values. And those are typically what are used when we try to get the cutoff frequencies extremely low. And when I say extremely low, we're really looking at cutoff frequencies maybe 100 kilohertz and under. Above 100 kilohertz, we use tubular, solid tubular ceramics. And those can, like in the chart here, we show starting at 100 picofarads. That's a cutoff frequency pretty high.
Well, maybe you could share an example.
Yeah, so like you can see on the chart here, if you're looking at, say like right in the middle of the chart is a 1 megahertz line. And that has, if you look up at kind of the red line, it shows 1,000 picofarads. So that's how you would look at, if you're looking at where your cutoff frequency needs to be, and what your insertion loss values need to be above that.
Okay, now you talked about different types of circuits in the past, and I think I've heard you talk about a C circuit. Could you explain that?
Yeah, C circuit is just a simple capacitive element that is, if you will, wrapped around the conductor. So the conductor goes all the way through the part, and the capacitance is applied between the conductor and the ground, which could be a plate, could be a threaded bushing, could be multiple different types of cases. The C circuit being a single component in the filter, will again, the total capacitance will define the 3 dB point, or the roll-off point, but a single capacitor will only give you a roll-off of about 20 dB per decade of frequency. So the slope after it starts to filter is only going to diminish 20 dB for every decade of frequency.
Okay, and then how about an L circuit then?
Yeah, an L circuit incorporates an inductive element, and the inductive element can be put on either side of the capacitor. So you know, L top, L bottom, or L1, L2 is typically how they're talked about. So two things. One is it's a 2-element filter. So again, the total capacitance will define the roll-off point. But since there's 2 elements, you're going to gain another 20 dB per decade of frequency in the roll-off. So if you look at a C and you go from 1 to 10 megahertz, it'll roll off 20 dB. With an L type, from 1 to 10 megahertz, it will roll off 40 dB. So you achieve much higher insertion loss quicker as you go up in frequency. L circuits are typically used where you have a fairly substantial imbalance of impedances. So maybe your input impedance is very, very low and your output impedance is very, very high. And you use the inductor to help balance that whole circuit.
Okay, and are there any other types of circuits that you might like to discuss?
Yeah, I think probably the pi circuit is I believe one of the most common in used when high insertion loss is required. The reason for that is it incorporates 2 capacitive elements instead of just one, and they're separated by the inductor. And this, again, it moves into a 3-element filter now, and that element will roll off at 60 dB per decade. So these are common items when you need to operate the unit at a certain frequency, but the unit is susceptible with frequencies that are not very far up in the spectrum. In other words, they're very close to what the operating frequency is. So using a pi filter, you can roll off the filter much quicker and achieve, again, the higher insertion loss values at a much smaller frequency range.
Is there maybe an example you could share?
Yeah, so again, looking at the graph, so you can see here that, again, if you're operating at 1 megahertz, and you have a filter that rolls off there, so you're okay. But if you can live with, say, you know, only 20 dB of loss out at 10 megahertz, then the C circuit will work fine. But if you're only down 20 dB, and that's going to cause interference with the system that you're operating, and you need to be down at 40 dB at 10 megahertz, then you need to go up to like an L or a pi circuit, so that you're achieving the insertion loss that you need, and the outside noise will not get in and interrupt your system.
Okay, and what can you tell us about packaging options?
So there's a lot of different packaging options. There's really kind of 2 definitions when it comes to that. The first definition would be individual lines, or if you will, it's a 1 conductor. You hook up 1 wire to it, and then there's a multiple line option as well.
Okay, So I take it then that the packaging options would vary based on the application?
It can, like I said, if you're just trying to power a unit, and it's say a DC, 12 volt, 24 volt, something like that. That can be just a single, like a picture here, a little threaded part, maybe at the bottom, or a solder-in part, that the power line can be soldered to, and ground is usually the case, or whatever the system ground is.
Okay, so now if this option is best for individual line applications, what would you say is best for multiple line?
Yeah, multiple lines come into play on a few different topics. Uh, when it comes to power, not all systems do they want the ground to be the case, right? They want the inner circuitry to have its own ground. So in those cases, if you look down like to the bottom left, terminal blocks can be provided in 2, 3, 4 pin type arrangements where you can bring power in, you can also bring the ground in along with it. The other options where multiple line is more common is not so much in power, but it is in signal filtering. Maybe from the outside world to the inside. Back in the day on say PCs, you used to have D-sub connectors that were filtered so that the inner workings of a computer would not be affected by, cellular tower noise and things like that. There's also, say in like RF amplifiers, you may have different sections where you have signals that you're passing from one part of the unit to another part of the unit, say in monitoring or things like that, that you don't want noise from the amplifier passing to those other sections. So a lot of times these like filter plates can be installed from one section to the other to prevent any noise from propagating through the unit.
Okay, well, thank you, Bob. Maybe could you summarize for us?
Yeah, I mean, the thing is, so feed-through filters are not as common as they used to be, in that the world today is a lot more digital than it is analog. But they're still very prevalent because things still require power. So that's typically the biggest use of them. And then, like I said, there is some signal conditioning or signal filtering in certain specialty type of applications.
Got it. And I think that we have time for one question. And the one that I received here is that you talked about various defined types of filters today. Do you also customize solutions?
Yeah, we do. We actually do quite a bit of that. It's hard to show that. Many of the applications that we custom design for are kind of secret, or maybe for the government, covered in NDAs and things like that. But we do probably 30 or 40% of the work we do in filtering products is custom in nature. And when I say custom in nature, it can really be almost anything that customers bring. Everybody seems to have their own special needs and wants, and we try to give them what they want and need.
Well, that makes good sense. And maybe that kind of is a good segue into the bullets that are on the screen here that really do kind of speak for themselves. But I get the sense, Bob, that Quantic Corry is as much a solutions provider as they are a provider of components. Does that sum it up?
We would like to think that we are, and we like a good challenge. So,
Well, there you go. Well, if you are a customer and you have additional questions, we would love to hear from you. And you can call our engineering hotline. The number is on your screen, 724-940-7556, extension 276. Of course, there's no cost associated with these conversations. And for those of you thinking ahead, the next Tech Talk will be on Tuesday, September 10th, and it will be all about subsystem designs. So thank you so much, Bob, and thank you all for joining us.
thank you, Paul.